Today, we are diving into one of the most incredible moments in the history of science. It's all about a single idea that totally reshaped how we see the universe. And we're going to explore it through the lens of Richard Feynman's brilliant explanation of Newton's laws, straight from his legendary lectures.
I mean, just think about that for a second. How did that happen? How did we go from looking up at the heavens in total confusion to understanding it like a predictable clockwork machine? Well, the answer lies in one incredibly powerful idea that Newton unleashed on the world.
So that's the big question, right? How could one single rule explain everything from an apple falling from a tree to a planet orbiting the sun? The story actually gets started a little bit before Newton, with a scientist who managed to solve the first piece of this massive puzzle.
And that scientist was Galileo. He gave us the principle of inertia. Basically, if you just leave an object alone, it's going to keep doing what it's already doing. Simple enough. But that left this huge, glaring question hanging in the air. What happens when things aren't left alone? What happens when a force gets involved?
And this is where Isaac Newton walks onto the stage. He gives us what you can think of as a universal key, a single method for figuring out how motion changes. Now, to really get this key, we have to be super precise with our words, just like Feynman would demand. So let's nail down the crucial terms.
First up, momentum. And look, this isn't just about speed. It's the total quantity of motion something has. Think about it. A bowling ball and a tennis ball rolling at the exact same speed are going to have very different effects, right? That difference is momentum. It's the mass times the velocity.
Which, brings us right to mass. Mass is just the measure of that inertia. It's not about how heavy it feels. Not really. It's about how much it fights back against being sped up or slowed down. You could almost call it an object's inherent stubbornness.
And this is where Feynman points out a super common trap, confusing mass and weight. Your mass, your inertia, your stubbornness is the same everywhere. It's the same on Earth as it is on Mars. But your weight, that's just the force of gravity pulling on you, and that changes depending on where you are.
And finally, we've got force. A force is just a push or a pull. It's any influence, literally any at all, that can change an object's momentum. If you see momentum changing, you can bet there's a force behind it. So all these pieces, they snap together perfectly in Newton's second law. It just says that force is equal to how fast the momentum is changing over time. That's it. This beautifully simple statement, that's our universal key. So let's see what it can unlock.
Okay, let's put this key to the test. Our first lock is a simple everyday problem, a weight just bouncing up and down on a spring. Before Newton, trying to describe this motion precisely was a nightmare. After Newton, it's actually a pretty straightforward calculation.
Now, to use our key, we first have to know the specific rule for the force we're dealing with. And for a spring, that rule is wonderfully simple. The force pulling it back to the middle is just proportional to how far you've stretched it. That gives us the F for our big equation.
And this, right here, this is the magic. This is the calculation engine that Newton basically invented. If we know where the mass is and how fast it's going right now, we can predict what happens a split second later. We use its position to find the force. We use that force to find the acceleration. The acceleration gives us the new velocity, and that new velocity tells us the new position. And then you just do it all over again. Repeat, repeat, repeat.
This whole process lets us build a little table, predicting the object's future one tiny time step at a time. We start at time 0, and boom, a tenth of a second later, we've already calculated a new position, a new velocity, and a new acceleration, all ready for the next step.
And what happens when you plot all those points you calculated? It's incredible. They perfectly trace out this smooth, beautiful, oscillating curve that we see in real life. The universal key worked. It turned the first lock. The method is a total success.
Okay, that was cool. But now, let's get ambitious. We're going to take this exact same method, the same key, and apply it to a slightly bigger problem. We're going from a little mass on a spring to an entire planet orbiting the sun.
I mean, this is the ultimate test, right? Can the same step-by-step logic that predicted a bouncing spring also predict the path of a planet hurtling through the cosmos?
And here is the absolutely amazing part. The calculation engine, that 5-step process we just walked through, it stays exactly the same. The only thing we have to change is the rule for the force. We just swap out the spring force and plug in Newton's law of universal gravitation instead.
So, we hit go on the program again. We give the planet a starting spot and a starting speed, and then, step by tiny step, we calculate its future x and y coordinates out there in space.
And when we plot those points, what do we get? Not some random scribble. We get a perfect, elegant ellipse. This is the exact shape that astronomers like Kepler had observed for centuries but could never, ever explain why. Newton's law, powered by this simple calculation method, finally gave us the answer.
So what is the grand takeaway from all of this? What's the big deal? Well, Newton didn't just give us a law, he gave us the power of prediction.
Think about this number, 2 minutes. Using the very same step-by-step method we just talked about, a modern computer can calculate the entire orbit of Jupiter, and I mean including all the little gravitational tugs from every other planet, to an accuracy of 1 part in a billion, and it can do it all in about 2 minutes. That is just a staggering amount of predictive power.
It's just like Feynman said. We were suddenly armed with this tremendous new power. The universe was no longer just something to watch. It was something you could actually compute. Its future could be known.
And that leads us to the final, really profound question at the heart of this whole revolution, this idea of a clockwork universe, a universe that's governed by fixed laws. It forces you to ask, if we can predict the motion of planets with that much certainty, what are the limits? If we know all the rules and we know the state of everything right now, is there anything we can't predict?